Welcome to the Databricks Skill Builder series. We're glad you're here.
Okay, everyone, the webinar has started, the recording has started. So, hi everyone, I'm Carrie Ross. I'm a solutions architect here at Databricks. And today we're going to talk about LLMs, Dolly, ChatGPT, and kind of a history of NLP, how we got to where we are and where we think it is going. And this has a Databricks slant at the end, but at the beginning, we're just going to talk really about the history of NLP. So this presentation started because we released Dolly at Databricks in March, and we'll get to what that is. And I saw that a lot of people were kind of wondering, how did we get here? How did we get to Dolly? How did we get to this LLM world and ChatGPT? And so that's where this presentation started, and then it's just continued on since then. Okay. So really, like I said, how did we get here? It's a brief history of natural language processing, some of the common terms you're going to see in natural language processing, and really with the intent of understanding what the current state is, but also where we think it's going and how we can get the most benefit out of natural language processing, generative AI, LLMs, etc. Okay, so I'm going to start really basic for some of you, but I like to level set up what is AI and how does this relate to ChatGPT? Now, there are a lot of different definitions of what is actually artificial intelligence. This one here is one from a textbook of when I was in grad school, and it's this idea of artificial intelligence is systems that think like humans, systems that act like humans, systems that think rationally, and systems that act rationally. So really what this is we've had machine learning, we've had computer programming for a long time. I would argue that really with the generative AI world and ChatGPT is we have gotten to systems that act like humans a lot because we have this chat, this really first time in a long time that things that just actually chat. We've had chats for a long time, but they're just more interactive and they feel much more human-like. So this is just the Turing test that was, from the 1950s. That was the basis of computer needs to possess NLP capabilities to really pass this Turing test for NLP. I'm going to pause for 1 second. Hold on. Okay, so then we come to natural language processing is really required to enable machines to communicate successfully in English or other languages. So what is ChatGPT? So this is a funny thing. My fiance is a veterinarian and he texts me all the time to say, what does ChatGPT stand for again? And it is Chat Generative Pre-trained Transformer. So we see here that, we have these couple words of generative, pre-trained, and transformer. So this is used in everyday language, but what we're going to talk about is the generative nature and what the transformer is and how we actually got to this point. Okay, so, what is the transformer? So I have this slide here of the history of how we started up here in vision and then down here in language, and then just how this is just the progression mostly of language, and I've a little bit overlaid them. And what I really want to point out here is over here in language in around 2017 is we had this early transformers. This was a fundamental change in the architecture. But what I also want to show is we see that vision has actually been using the CNN and RNN for a while, and there has been cross-pollination across these models. We're going to get into a little bit of language, what makes it different than vision, but I like to remind people that even though we're talking about generative AI, we're talking about the history of natural language processing, vision and language are tightly, they grew out of this solving similar problems and similar technology. And so I do like to remind people that a lot of people are looking at these language problems, but there are a lot of benefits that can go into the vision world. We'll go later and look at Hugging Face, which is a marketplace for models. And you'll see that there's groupings of vision, there's groupings of language, and how you classify these. But I really also like to talk about these because there are many architectures and there are many tools in the toolbox. And at Databricks, we like to be very flexible so that you can choose the right tool to solve your problem. So I'm going to go into a little bit of how we made this leap from LSTMs and transformers, and we're going to actually talk about what these terms mean. This is, an intro. Some of you probably know this, but CNNs and RNNs and LSTMs and why they actually changed this transformer, and when we're going to get to this ChatGPT. Okay, ChatGPT and the Muppets. So, there's often discussion on when we talk about ChatGPT and we talk about transformers and generative, build your own or use a pre-trained model or build your own. So I do want a discussion of where this history was and a little bit different view than we had before. Oh my, so my slides didn't show up here, but again, I'm reminding it ChatGPT is chat generative pre-trained transformer. But what I want to show here is this is the family of Muppets, a Transformer Muppet family. I've got a link down here to this family. So when we look at this model, we can see that we started with the semi-supervised sequence learning. We're going to talk a little bit about that, where a lot of models started with this here. This is before deep learning. So before we had deep learning in those CNNs and RNNs, there is a lot of counting. NLP has a shocking amount of just simply counting words where they started to. So a lot of models built out of the semi-supervised sequence learning, and then we built this BERT. If you were working in the industry in 2016, anyone that was talking about NLP was talking about BERT. But if you look here, we have GPT of this generative pre-trained model. We have these larger models that come out here, GPT-2. We have GPT-3 now, obviously, but we also have these other models that do different things and they do different things well. So again, this is just to remind people that there is a large ecosystem out there. It's not just the GPT. ChatGPT right now is the best in class for performance, but there are many options out there. Okay, so I'm going to use an example when I was talking about why, computer vision versus natural language processing and what makes language such a challenge. This came from back in grad school. It's a bit of a dark example. I don't know why this is showing up with yellow. It was supposed to be green, but here we go. We have this example of language. The teacher said the cookies made from the children were delicious. Okay, the cookies taste good. We like that. The cannibal said the cookies made from the children were delicious. This has a very different context based on these two words of teacher versus cannibal, but to really understand, you need to have this context of what's here in yellow. Sorry about the color. The made from the children means something very different based on looking backwards in time. So if I was just processing word by word and say counting verbs and adverbs, adjectives, and all the things I forgot from English class, this is your noun, teacher and cannibal, but you really need to know this made from children part to understand what, you need to get down to this part of the sentence of made from the children to understand how dark this sentence is and how innocuous this sentence is. So this has this look forward, look back aspect that many other parts of natural or machine learning, computer vision don't have. So what we're going to talk about is what the history of what has been done to work through. This is one of the fundamental problems. So we're going to start about when everything wasn't so deep, when neural networks were not the state of the art. As we go along, and this is really flying through a deep subject very, very fast, but we want to talk about the ancestors to NLP because they do come up, and you see when you look at the history and when you start diving into some of the different ways you do modern language processing and generative AI, you're going to see a lot of these words. So like I said, NLP has a lot of just counting. There's this concept of bag of words, and you literally throw everything in. You don't keep order, and you just count how many times I said the word cannibal. That might be important. You might count how many times I said teacher. That might be important. And then you create a vector of the space. And so another fundamental problem, we'll see this of why it takes so much processing to do natural language processing, is because you have to take words and somehow convert them into math and numbers, because that's what computers think in. So in this one, it's this way of converting is you're counting. And n-grams are doing sequences of words. So you have just some different vectors for each document. You can imagine how this gets large, of the cat sat, the cat sat in the hat, etc. And you're just doing the counting on the documents. I'm not going to go too much in these. We do have a link here, but the next one is the count base, but then you have prediction base. You'll see a lot of this thing of out of vocabulary. OOV, you see this when you're looking at different models, and modern models handle this really well. They have this thing called zero shot, and zero shot means for one of the first times, models are making pretty good estimates without having seen the information before. This is a leap forward, and these ancestors had a problem with out of memory, not having the training. But these were these non-deep learning counting. I am going to pause and say, just because things are old doesn't always mean they might not be sufficient for a simple project. And the example is linear regression has been around forever and a day, and there's some obscenely high number of models in production that are actually based on linear regression. Why? Because it works, it's simple, and it's understandable. So some of the trade-offs when we go later and start to talk about the architectures that you want to think about when you're building these models. So what this slide is, and this is just really for reference, is we're looking again of what's called dense vector representation. This comes into play in modern because you're going to have word embeddings once again to go from words over here into a vector space. So what you're doing is you're projecting of how we do words into an n-dimensional vector space so we can do math. And if we're looking here, what's trying to be done with using word embeddings and dense vectors is a way of saying cat and kitten aren't the same, but they're probably pretty close. They're probably closer than dog, and they're probably closer than houses. So now that we have this in a vector space, we can start doing math in n dimensions. So this is a visualization in 2 dimensions, but word embeddings can go to n dimensions based on how you do your actual embeddings. When we take a look at Hugging Face, which again is a marketplace for a lot of these libraries and models, you see that there are many ways to do these types of embeddings. There are many best practices that go from looking at doing maybe a proof of concept versus production and speed. So that's why this is in here with this link, so that you can just go dive deeper should you be interested. Okay, so we started the world counting. Counting's great. We all know how to do it. We understand it. We got more complex because we decided we want to do distance metrics on words. So now we're going to this n-dimensional vector space. We're getting not deep neural networks, but we're adding more complexity and we're adding more processing power needs. So things, if we look back at that original slide, things go deep with neural networks with RNNs, LSTMs, and CNNs. We're going to go into those. The recurrent neural networks, long short-term memories, and convolution neural networks. And these are all used to solve different problems that we've seen along the way. Okay, so the big thing about the recurrent neural network, it is recurrent. It has a feedback loop where you do the output of your weights. So your inputs are down here, your weights are up here, and you're doing a loop back and feeding. If you're going to train your own generative or do fine tuning in your own generative models, you're going to hear something we talk about batch size and epochs. They're both terms that you hear in neural networks and deep neural networks. And what it is when you start thinking about we have to feed back data into itself, we're going to have to break the data down into a smaller size. That's your batch size. And we're going to have to figure out how to deal with this feeding back and also how to push the data fully through. So your batch size, you're going to break it down into different batches and feed it through. This makes distributing recurrent neural networks very hard. Databricks, we have libraries that help with this, so you absolutely can, but natively it is a hard scaling problem. And then the word epoch that you're going to see, and that is part of if you're doing any fine tuning of your models, and again, we'll talk about that. Epochs are how many times you feed your full data set through whatever network you have. So you've got batches where you break it up, and then you have epochs saying, I want to push all my data through, run a bunch of stuff, find a bunch of weights and biases and all these fun things, and then push it back and feedback errors. And then you're going to push all the data through again and keep iterating to get better. And I bring that up because it does come up when if you go and dive into what we did with Dolly with fine tuning, people do ask about how many epochs. I think we trained it with 3. Pretty standard is 3 to 5. But when I just said you push your whole data set through, you can imagine this gets time consuming and expensive. And then there is a diminishing return to how many times you do this. This is part of what still makes, deep learning challenging, is these are the parameters that you must tune and figure out what works the best. And there are numerous techniques to do this beyond the scope of this of how you actually tune these. But I just want people familiar with these terms that do come up, even though we're talking right now about recurrent neural networks. So recurrent neural networks had this problem with memory. So that's why I brought up that first thing about cannibal, is you need the end of the sentence to really get context for the first of the sentence and vice versa. And if you imagine that sentence, you could flip the sentence and put the cookies made by the children were delicious, said the cannibal. So if you flip that, it has the same meaning, but now you're going to have to figure out how to have your network do this forward and back. So what LSTMs, there's a lot of LSTMs still in production. This is what I learned in grad school because it was state of the art at the time. What this has is it has these things called forget gates. And what it just really does is it says, I have a longer short-term memory. I can look further back in my language than I could before with recurrent networks. There are tricky things that happen with curl networks that you see here. That has to do with the number of what's called hidden states in the middle. So this gets pretty deep into the neural network world, but that's what this problem was solving. It was the next evolution. And again, a lot of LSTMs in production. Okay, convolutional neural networks. I apologize for not having pictures for these. I thought I did and I don't. Convolutional neural networks are really, if you think about math and matrix math, it's a way of convoluting, of layering information and getting information from previous states. So we have here that, it computes vectors for a possible phrase regardless of grammar. So, this is showing that it's not going to be linguistically because of the way convolution works. Again, there's a link here if you want to look at it. But if you think about it, it's a way of layering and looking at matrix math. And again, it still has the neural network. It still has the deep states and the training issues that we talked very briefly about. CNNs really became state of the art because they're fast and they're very good for some things like text classification, sentiment analysis. What they weren't good at is what we talk about with generative AI, generating new text. So again, lots of links that you can go deeper. Okay, but landmark in NLP, the Transformer Architecture. This is one of the biggest game changers we've seen in deep learning since the advent of deep learning. And I'm going to show a little bit the architecture, and I'm going to show a little links to the paper that first put this out in 2017. And then that's where we saw in that beginning the Muppets, where BERT was based off of that, and then GPTs. And this logic has solved a lot of problems that we just had before. Okay, so into the weeds of transformer logic. And then we're going to talk a little bit about the architectures, but this is one of the things I like to talk about in transformers. There are encoders of how you encode the data, how you take those words and go to numbers and encode it, and then how you decode it. And then there's some that do both. So what they kind of group into with this logic of there's called this autoregressive models that are the decoding type of transformers. And these are best at that natural language generation, predicting the next word. And the GPT family of transformers are all based on this decoder type of transformer. We have more information coming. The blue boxes are where we were. A lot of these were built off of these. And so these are the natural language understanding. So the comprehensive understanding stands for the bidirectional encoder representations. And bidirectional means just that, back and forth. I put this up here because this slide to me just made I like looking at the same information a lot of ways when you're trying to go, what is this? Why do we have so many of these things? Everything has a limitation, and we're trying to minimize limitations and maximize our results. So I've got a couple more slides where I'm going to talk more about here. What did this thing in 2017 do that this is transformer? It's still a deep learning model, and why this has now enabled all of this. And then we're going to also then look at what the different groupings of these different types of models that are out there. And I'm not seeing any hands raised, and I know it's hard to type things, but please do, if you have questions, if you want me to dive deeper on any of these, please do let me know. And then again, we have links for all these so you can go as deep as you want. Okay, the Transformer Architecture, Attention is All You Need 2017 paper. This is the key difference in this architecture, is the attention in the feed-forward network. So why we need to talk about this for modern architecture is that input tokens are very important in the embeddings. So tokens are how we take a sentence and break it up. So the simplest way you can do a tokenization is you take a sentence and you break it up by spaces. So every word I'm saying, you break up and use that into a word. That word's now a token. And then you feed that into the embedding that we talked about. And again, embeddings is how we go to that high dimensional space. These two are massively blow up your data sets. But the reason we were looking at this here is these networks here are feed forward. The RNNs and CNNs have this feedback loop. Now, to deal with this feed forward is you have to add this attention. So in here, we have different things to add this attention in the feed forward network. And this paper is actually very, very readable. It's, 6 pages is kind of your standard transformer. I recommend reading it at least once because you'll get an idea of how this did change. But this is the way that we have dealt with positional encoding while only feeding things forward instead of looping back. So the summary is this is able to do faster. It solves some of the problems of adding that look back that you need with language, while also being able to scale better than we've seen before. Okay, so here we go. This is a great blog down here, and I did actually verbatim copy these words from this link. I'll put them in quotes so I give credit where it's due. But it's that sequence to sequence neural network. So we didn't talk about sequence to sequence, but that was that whole pre-deep learning. And then we added the neural network. The input text is encoded with tokenizers to a sequence of integers. So the input tokens. So that's down here where we're doing this embedding. When you go and start looking at architectures for generative AI, doing your embeddings and doing your tokens is a lot of the work and a lot of where you're going to be able to see different performance and get these type of models to work on your type of data and not have to rely solely on ChatGPT. It's and I talk to a lot of customers and they're asking about architectures and which models to use. I cannot stress enough how much this type of embeddings and your pre-processing can change and improve your architecture and your usage of whatever model you decide to use in this space. Now I'm pausing here because We're going to talk at the end, time permitting, again about architectures, but this is the underpinnings and the foundation, and this is the part that a lot of, when my mother talks to me about ChatGPT, she doesn't think about this stuff or what's going underneath, but the way a lot of us interact with ChatGPT or any other model really is in what's called these playgrounds, and you go in and you type your question and you get an answer. That's great. What's happening under the hood for the companies that are using their own, and even if they're using a state-of-the-art ChatGPT, if they want to bias it, and I mean bias in a very good way, to their own data. So if you're a chemical company, you know a lot about chemicals that's more specific than ChatGPT would. So you're going to figure out a way to use these embeddings and these vectors of this data that you have, feed it into the network to bias it in a way that you know is good from your documents. So again, I'm using bias in, a positive way that's not usually used. So this is the general of, you start here with your tokens, you have these embeddings that are used several places. And then you have output tokens, and then you have to decode it back. So I recommend this model, or this link, or this blog goes through this very, very well. So this is, this couple of papers, that paper is the fundamental of that transformer. We haven't really talked about that pre-trained in general, of where we say ChatGPT, where that pre-trained word comes in. We'll talk about that really briefly when I'm looking at these models, but this is the crux of the, let's see, natural language processing in 25 minutes history. So I know I've given you a whirlwind, but again, what I want to stress is, I'm going to go back to, we got to this point here, the ChatGPTs, where it's really been, one of the first truly AI feeling things in a long time, but it's been built on a lot of these models. Understanding this little bit of history will help with understanding how you're going to use these, whether it's ChatGPT or just generative models, or LLMs, large language models, are all based on some of this history, and a lot of those learnings are still being used of how we do the pre-processing for our current modern models. Okay. So the word pre-trained. I think everyone's probably heard that ChatGPT costs millions, or was it billions of dollars to train, because it's trained on pretty much everything. So what we're going to talk about now is how we actually either use a pre-trained model, which is ChatGPT. There are ways of accessing those pre-trained models, and there's been a really hotly debated, and it's actively changing right now, of using proprietary models versus open source models. We're going to talk about this, but I have this link here. I'm going to what I actually want to go to Hugging Face really quick here. It's, as I have on this slide here, it's build, train, deploy models from open source machine learning. So what I want to show is over here on the left, I just went to the huggingface.co. There's models, there's data sets, solutions, etc. But this is where I was belaboring this different groups of tasks that you're trying to do, because in the end, we're trying to solve problems. So there's multimodal tasks, computer vision, natural language processing, audio, tabular, reinforced learning. And then you'll see in here, we have, when you click on any of these, you're going to see all these different models that are out there. That's why I want people to start thinking about, Llama's gotten a lot of press lately, but these are the different, and zero shot classification is an interesting one. Zero shot, which I briefly mentioned, is where these models can perform well on data they have not seen before. So this is very different. So this can be a little bit overwhelming, but they do group them for you. And then there are a variety of places and resources. We have one that helps look at the state of the art. What is the state of the art models right now? I do have that link in our references that I'll be sending out. I want to pull it up quick. And so this over here, we have this link. It's on our Databricks. It's in the back of this document that I'll be sending out. Best in class open source models for generative AI. So, this was updated last week. So this is, text embeddings and transcriptions and image and code and the quality optimized, balance, speed, and some notes. We are keeping this up to date. This does not, this is based on open source. So there are proprietary models. I actually have a slide on that. We're going to talk about that in a second, but I just wanted to know our customers, we know that they're, struggling with some of this. And I'm going to show here, this is by us, and you don't see Dolly on here. And I'm going to explain that in a little bit and what Dolly actually is, since there's a lot of splashy press releases around Dolly, and it was game changing, but not necessarily for the reasons that people might think. Okay, so generative AI is here, transformers are here. Now, what do we do? So I'm going to give a couple of different viewpoints here. I just had that slide, but we're going to go into it. Many are saying, Databricks is saying that this is an iPhone moment in machine learning, that this is going to change our world. And I'm also going to talk about a little bit of, is this hype and what should we do? And then talk about why we released Dolly. Okay, so innovations. I really apologize. So my text really got weird on something I did. But innovations don't become technology revolutions once they're democratized. There are words here that I can't remember, but and really this is the idea of, we have seen computing was around the 1950s, but it wasn't until the PCs got into everyone's hand that the innovations became this technology revolution. Why? Because computing was at first, it was this very big mainframes, very specialized, and we got the PCs and we made it much more user-friendly. Same thing happened with the internet. 20 years later, we got the web browser. So we went here, this is 30 years, this is 20 years. Deep learning was 2012 and, 11 years. So the speed of innovation is picking up. I've been an engineer for 20 some years and I've never seen it move this fast. It's exciting and alarming. So what we're trying to do at Databricks is help our customers see where the industry is going. We're building our platform to allow the flexibility to do what you need to do with the models you need to do, and know that the world is changing fast. So this is, it's considered this iPhone moment, that this generative model. A counter argument that I do want to bring up, because I think it's valid, is the Gartner AI hype cycle. So, innovation trigger, peak of inflated expectations, up here, and then you go through the trough of disillusionment and slope of enlightenment. Computer vision had a head start. It's a little bit easier for the reasons we talked about, and it's able to use older models. So it's got a lot of productivity. Cloud and AI. We go up here and we've got generative AI according to Gartner up here at the peak of inflation. Now, I'm not saying, I firmly believe that transformer logic has changed the world and will, but it's not going to solve every problem by just using the SaaS models that are out there. And that's why I wanted to belabor the embeddings and the data and the process that goes into these models. It's not push button, but it will drop a little bit as people don't design. If people aren't designing their systems, they're not going to get the results that they thought they were going to. Then you hit down here in the disillusionment and then it picks back up. So this is normal. It's something to think about, but at Databricks, we really do believe that it is an iPhone moment, but keep this in mind so that you are planning your systems to go through this trough of disillusionment and build, and I have a slide and a couple that talks about how we can minimize this a little bit through our architecture and our platform decisions. Okay, so I said I was going to talk about what Dolly is, and I have this link here. And this is the whole democratization of ChatGPT with open models. Like I said, there is kind of a battle going on between open versus closed and pros and cons. With that, we're going to talk about that in a little bit. But what Dolly is the first open source LLM tuned to human generated instruction set. So many words. What that means is we didn't take a proprietary model that costs millions or billions of dollars to make and then use that. We use one of those open source models that are available, tuned it on a data set that was actually created by Databricks, so we could guarantee that it truly is open source, and then donated both those to open source. So on Hugging Face, you can actually get Dolly and you can get the data set that we created here over in the data sets. It's a 15K data set. 15,000 is not that big. So there we go. Databricks Dolly 15K data set. So we open source that. So the big reason we did this was to show that you can take open models created in research, have a reasonably small data set, have a reasonably small model, and get performance out of it. Now, Dolly is not state of the art. We don't sell Dolly. It's just sitting on Hugging Face, so you may use it. It's not the one we recommend anymore because the world changes fast. So we have quite a few links on this Dolly blog post because we did Dolly 1 in March. Dolly V2 came out in April because this March one was not trained on an open data set. The V2 in April was trained on an open data set, which means it's open for anyone to use. So that's the legality part. And the big thing is that you got generative AI performance building off this foundational open source model for hundreds of thousands of dollars to train in hours, not millions and billions in years to train. So that's the whole reason we did it, for an experiment and example of what is possible. Oops. Okay. Skipping around order. Okay, so with this open source, this is a timeline of what we've seen. You know, Facebook had the llama for these were non-commercial use, and then alpaca, and this is where we are here that we did this open source. And then since then, Mosaic MPT and Falcon have actually become more state of the art. If you look here, this happened pretty darn quickly. This is a medium size. It's 7 billion parameters. That's now what we consider medium size. But these are ones that you can take. They're open source. You can use your own. We're going to talk about architectures, like I said. But they're now commercially available. So this was that turning point. This is why Dolly is important, not because it's the greatest model. It was done quickly. But since then, these are great. These models outperform and they are seeing a lot of benefit to our customers. So this one I want to talk about is, you know, I love talking about technology all day, but in the end, companies pay you because you get business value. So right here, when people talk about ChatGPT, you know, Microsoft, OpenAI, when you go and look at OpenAI, you're going to see a list of models that they use in OpenAI. I think it's 4 or 5 right now. There's, of course, ChatGPT, but there's a few others that are underneath the umbrella of OpenAI. These are proprietary SaaS LLMs, large language models. This is the whole pro and con of how do you want, which one do you want to use? How do you want to use it? And again, there is no single model best for every use case. The biggest thing when I'm talking to customers, I want them to think about is, where are we right now? What can you do to start using this sort of technology in your architecture? and also build in that flexibility for the future, which is unknown. So I want people to foresee the future and plan for it, which is not easy. So that's why we have flexibility. But I do like to stress that, proprietary versus open source, do the right thing for your current business use case and plan for things that are going to change. I have right here the modality and the application. This is from this terribly colored link, Exploring Opportunities in the Generative AI Chain. This is a McKinsey report that link works, so you can click on it. I highly recommend reading this McKinsey report because they're talking about how do you get value from it. This is a clip of theirs of these different types of modality, and you're probably possibly going to want a different model for these. So you might have several applications and you're going to have different models. Your architecture, your underlying platform can be the same, and you can pretty quickly drop in and out different models. And we're going to get some architecture diagrams so I can speak to this a little more clearly. Okay, so again, this is just a prettier picture than I had before of looking at the proprietary, OpenAI, ChatGPT, and some of the open source LLMs. There's privacy, quality, cost, latency. These are your standard architecture decisions you're going to have to make anytime you're building an AI system. Okay, so I mentioned briefly before architectures and playgrounds versus productions. Playgrounds are that thing where we're typing in a little window and I get an answer and it looks really, really easy. That's over here in this playground of users, prompt, LLM response. This is what people not in technology think of. This is one of those things that sometimes people are like, you're telling me I have to plan an architecture. Why? Isn't it just this? Well, as we build in complexity, or we have different business use cases, this right here says fine tuning. And so over here, you still have your user, but you're going to take a base model or a foundational model. You can use OpenAI. You can fine tune OpenAI, by the way, or you can use something like Hugging Face. You're going to take your own domain data and do this thing called fine tuning. That's why I yapped about epochs and data sets and stuff. We open sourced how we fine tune Dolly. So you're able to get that code and you can actually see those. It's not that hard. It's a script that you put in and look at, and then you get your own LLM, and then you get that prompt and response. So the user gets the same feeling. A lot of the chats that you're seeing already being used out in industry, our AI assistant, for instance, you have a lot of this architecture. It's a very common architecture problem, or architecture design. The domain data, this is where you're going to need that pre-processing. It's why I talked about tokenization and context and all that, is because you're going to have to do some work here. And then there's different ways that there's pros and cons to this architecture. Context embedding. So this is another one where you have, again, your users doing this, but we're going to walk through. You have your prompt. You have this orchestrator that does this called similarity search, where you're going to look at your own data that you have, your domain text, how you do your embeddings, you put it in this database, you add it to matching documents, and then you feed it into this LLM, you get a response back. So if you look at this architecture at a high level, it's got a lot more to it. Pros and cons, there are lots of them. This one means you can use this base foundational model. You can actually bias it, what I was talking about before, to your own data, and you can get a response back without doing this fine tuning. This one doesn't have those things like epochs and all that stuff you have to do with deep neural networks. But the trade-off, one of the trade-offs here is latency. Pro of this one, you can keep this updated a lot faster than you can probably retune a model. So these are, my text didn't show up. These are 3 super simplified ways that you can use LLMs in production. There's not a right way or a wrong way, but it's a way of thinking about it's not going to be quite as simple as maybe this that people first think. There are some ways that you want to think about how you want to manage your domain data, how you can get a benefit over your competitors. Okay, I've got 10 minutes left. I'm going to go through a couple of slides of what we're doing at Databricks with generative AI. Okay, so a lot of my belaboring of this is that generative, even with these open source models, you still have your ML problems of ML ops and LL ops and feature engineering and managing your data and managing your responses. So it's really that you need to think about how you want to do your ML ops, your LL ops. You're always going to have to prepare your data for AI, evaluate, train, serve the data, serve the AI, serve the data, and monitor. We have built in a lot of new features for this. So again, we work with across all these models, so you don't need to choose. You don't need to know today what you're going to do tomorrow. We actually cover a lot of these. So proprietary, open source, and of course, all of our favorite classical algorithms like linear regression, my favorite. And we have built in more with LL ops. If you want more details on this, I didn't want this to be the focus, reach out to your account team. We have whole details of what we're doing for end-to-end LLM operations and also ML ops. If you haven't ever had that discussion, we have a lot of really neat ways of managing this in production, because a POC is very different from production. We want you to have the ability to do both. Your quick and easy experiments and also go with production. The one thing I want to talk about, we have recently finished this purchase of Mosaic ML. Mosaic ML has been, they put out, oh goodness, I just forgot. They put out MPT, I couldn't think of the name. Mosaic ML put out MPT. It's one of the best open source models right now, but we did purchase them, and this is just one architecture I wanted to highlight about some of the components we've talked about. This is Replete blog. They have a great blog of how to fine tune your own, and this is their architecture. But if you look, this is where we started talking about, we do have this Hugging Face integration, and then you have to, pre-process and do the tokenization and do that training. There's sampling, and then Mosaic was helping with speeding up some GPU clusters. I didn't go into detail. Most of these need GPU because of that high density space that you have used with your embeddings and tokens. So that's part of the reason that you need these GPUs. And if you really want to think about, if someone asks, GPUs are really, really good at matrix math, and we do a lot of it in anything NLP. So I just wanted to bring that up as an LLM architecture, because we have that slide of what it actually looks at. We've got a few minutes left. So a couple more things I do want to go through really quick. So this is out of order. Okay, so if you want a way of playing, this is Dolly, and it's an older, like I said, it's not the state of the art. It's not something I would suggest even for your POCs. But if you go to this link and you have a Databricks account, you can go to dbdemos.ai, and then you're going to navigate through a couple of pages, and you'll see this little tile that says build your chatbot with Dolly. And we have the step-by-step how to do this, but you can install this LLM chatbot, and it's going to walk you through how we actually do this. This is the architecture that demo does of how you're going to do some basic download of data set preparing, converting embeddings, using a vector database. This is that architecture of using context embeddings to look up and how you do inferences. So I just wanted to show that so that you know, this is the link where you would go. It's going to use one of those architectures. When you follow the steps in this with this demos, this is just a library that you installed, LLM chat. It will start up a GPU cluster. These are the couple of things if you don't go through and use this Databricks install and just create your own GPU cluster, you can do that. A common issue is this XML reading file. This reading the XML file, your first couple of data pre-processing steps might not work. And this is just the link of how you need to install it into your cluster. But if you just follow these steps, you shouldn't have it. I put this in here because people like me go, oh, I'll just create my own GPU cluster. Now it doesn't work. It's this XML file. So just a couple of notes, because this can get pretty abstract. That demo architecture that here really goes through this pretty nicely of those common components. I would guess it takes an average person, if things go well, 1 to 3 hours to just get this demo fully running. 1 hour if you don't run into any XML problems, 3 hours if you do silly things like I do. It may be longer if you're new to Databricks, but you know, that's a great resource for you to start working on some of these, figuring out this, index embedding, do this search. We do use LangChain. So I put this in here. It's pre-process, embed, similarity search, LLMs. This is a common thing used in examples and POCs. There are pros and cons about going to production with LangChain, but it's a way of looking. It's a good resource here that I wanted everyone to have. Okay, so, oh, I'm sorry, I just saw a question now. Yes, so in the back of this with the resources to run Dolly locally or on Databricks, yes, in the resources I have this here, and then I have a whole nother sheet that's going to probably give you more resources than you ever wanted. But these ones here will do that using Dolly 2.0 and quickly evaluate. I didn't go into a lot of like weights and models and how all that works, because these are billion parameters, but that's one of the reasons we have built LLM ops into MLflow, the newest releases. So I hope that answers that question that someone put at 11:50. We have that. The person who usually sends out these documents is out sick today, so I think it might be a day delay before you get these documents, but you will get this recording and these documents with these resource links, because it is chock full of going down a rabbit hole of details if you'd like to. With 3 minutes left, can I answer any other questions for anyone else? Not seeing anything pop up in the Q&A, so I think we will call that everything. So again, if you have any questions about this, Carrie Ross, you can reach me at databricks.com. So carrie.ross@databricks.com. I think most of you have account teams. Please reach out to them. We do love talking about this really new technology that I think is really going to help a lot of us out. So thanks, everyone. Have a wonderful rest of your day.